Hello everyone, welcome to my talk on testing alternative runtimes with Node and Vitest. So this is going to be a deep dive into how we built the Cloudflare Workers Vitest integration, but the techniques will be applicable to other runtimes too. So as a quick introduction, I'm Brendan. I created Miniflare, a fully local simulator for Cloudflare Workers. I'm now a systems engineer at Cloudflare, specifically focusing on Workers dev tooling. So I've mentioned Cloudflare Workers a few times already, but what are they? Workers are basically a functions as a service platform. You write some HTTP handling code, publish it to our platform, then we give you a URL to run it. Our runtime provides standard APIs similar to what you'd find in a web browser for request and response handling. We deploy your code to all Cloudflare Edge locations, so your users get low latency access wherever they are. Importantly, there's practically no cold start time, because our runtime is based on V8 isolates, not containers or virtual machines. If you're interested in how we do this, there's a great talk from the architect of Cloudflare Workers, Kenton, called Fine-Grained Sandboxing with V8 Isolates. It should be one of the first results if you Google it. In addition to standard web APIs, we also provide runtime APIs for accessing the rest of the Cloudflare developer platform. For example, accessing key value storage. Here, storage is a binding to a worker's KV namespace. We can get, put, delete, and list values as you'd expect, and there are other types of bindings too, so things like blob stores, SQLite databases, and other workers as well. We use a custom V8-based runtime called Workerd to run your code, and then we build this thing called Miniflare, which is a Node library providing a JavaScript API on top of Workerd, and it also provides local simulators for the rest of the developer platform, like Workers KV. So now that we've explained the basics of workers, let's talk about tests. Say we have this worker that adds two numbers together, and we'd like to write tests to verify its behavior is correct. There are a couple of ways we could do this. We could either write an integration test that starts a local instance of our runtime, sends an HTTP request to it, and asserts on the response, or we could write a unit test that imports functions from a worker directly and asserts on their return values. To support unit tests, we need to access workers' runtime APIs inside the test runner, so that the function runs with the correct global scope. We provide a few different ways of doing this today, but they all have their limitations. So this talk is going to explain how we built a new system that supports both of these types of tests. Before we move on, let's review the key points that we've just covered. We have a custom V8-based runtime, kind of like Node or Dino, that implements mostly web standard APIs like browsers, so things like fetch, request, response, web crypto. But we also implement some non-standard APIs, specifically for the server-side use cases, like connecting to Cloudflare databases, for instance. So, with that introduction out of the way, let me give a summary of what I'm going to be talking about today. To start, we'll cover how Vitest works and how we can change where it runs tests. Then we'll look at how we added support for dynamic code evaluation to the runtime. Next, we'll look at how we put those primitives together to run Vitest in the workers runtime. After that, we'll look at ways we've improved the developer experience, starting with isolated per taste storage. And then we'll take a quick look at helpers for calling durable object instance methods directly. And finally, we'll finish off by focusing on declarative request mocking. So let's begin with an introduction to Vitest. Vitest is a very popular testing framework within the JavaScript community, providing very fast reruns with hot module reloading, snapshots, and mocks. Vitest is kind of split into two parts. There's the host that runs in Node and provides a CLI, sequences tests, and reports output, and a pool that spawns threads or processes to run tests. By default, Vitest uses a Node worker thread pool to provide isolation and parallelism for test runs. But because the worker thread runs in Node, your tests have access to built-in Node modules and globals and all that stuff. To run your code and other dependencies, Vitest uses a package called vitnode, and this transforms your code with Vite and then dynamically executes it in a worker thread. If we want to run tests inside workers, we need access to workers runtime APIs defined in our Workerd runtime. There's a slight problem here though, in that we can't really reference JavaScript classes across a process boundary. Instead, our approach is to run the entire test runner inside Workerd and use WebSockets for communicating between the Node host and Workerd process. How do we actually do this? Fortunately, Vitest provides an API for implementing custom pools. Pools export a function returning an object with a run tests function. The run test function accepts an array of project files spec tuples to run, and any files that should be invalidated because they've changed. To demonstrate what this would look like, let's build a simplified workers thread pool. So for each spec tuple, we create an RPC channel, and we use a message channel for communication here, but we could switch this out for a WebSocket. The create methods RPC function is provided by Vitest and returns an object with functions for fetching modules from the Vite node server and reporting test results. Next, we assemble data to pass to the new worker thread. We pass the test file that Vitest should run in this worker and the project configuration. We also pass the worker side of the message channel. Now we can actually start a worker. In reality, you'd use a worker pool implementation here, like Bacino or TinyPool, but we're just using plain workers from the worker threads built-in module. We want to keep this simple. In the worker, we import Vitest's worker script and then call the run method on it, with the worker data we constructed on the previous slide. We could start a process here instead of a new worker, and in our case, we'll actually be starting a workerd process here. But you could start any other runtime here as well, or you could like connect to a different machine, or do something completely different. So one of the Vitest pools actually does type checking. You don't actually have to run the test files as JavaScript. Finally, let's wait for a result message from the worker, and then store these promises in an array. And then we can wait for all of the promises to resolve and report any errors as an aggregate error. And with that, we have a basic thread spool. We can use it by specifying the pool property in our Vitest configuration. Note that we can also pass options to the pool with the pool options property. Running npx vitest will use our pool and run our test successfully. So let's overview what we've covered so far. The key points are Vitest uses a node host to orchestrate tests and report results. Pools decide what to do with test files. In this example, we've run test files in a node worker thread. But for the Cloudflare Workers integration, we'll want to run them in workerd processes instead. The test runner code that Vitest uses is designed to run in Node, but we'll be running it in a workers environment instead. Cool. So I mentioned that Vitest uses dynamic code evaluation inside the test runner, so let's explore that in more detail. If we go back to our previous custom pool, let's look at the messages being sent between the pool and the worker. We'll see there are a few different RPC methods. The two most relevant for us are fetch, which transforms a path with Vite in the host. So it essentially bundles all of the code at that path using Vite, then returns the result to be dynamically executed in the worker. Note, these imports have been replaced with special calls to Vite functions, and this is how Vite implements hot module replacement boundaries and module mocking. And the other relevant method is resolve ID, which takes a specifier and a referrer, then returns a file path to a module. If this is in the node modules directory, Vitest will try to dynamically import this. So with this in mind, we have two requirements. We need to be able to execute arbitrary JavaScript code from a string, and we need to be able to import arbitrary modules from disk. For security reasons, the worker's runtime explicitly disables dynamic code evaluation in production, so we need to figure out a way to do this while retaining these security guarantees. To solve this problem, we added a new type of local-only unsafe eval binding. This allows you to call indirect eval, or the new function constructor, or a couple of other things as well. And by adding this as a binding, we can control which code has access to eval. This is very important for tests, as we don't want code that relies on eval to pass tests locally, but fail when deployed. We can see in this example, we're passing the unsafe eval binding to the evaluate function, but not the double function. So only evaluate can call eval. This is a very basic form of capability-based security if you're familiar with that. This works great for JavaScript code, but unfortunately you can't eval ES modules, so we couldn't use this to implement module loading from disk, unless we kind of like built our own module loader in JavaScript, but ideally we just reuse workerd's logic for this. Usually workerd requires all modules to be specified up front, which makes sense if you're operating a functions as a service platform, where you'll be sort of uploading code to the platform. Whenever a module imports another module, we resolve the specifier relative to the referrer URL, then look for that in the registry. In this case, the specifier is maths add, and the referrer is /index. So we find the module in the registry, make sure it's initialized, and return it. However, if we add an import to a module that doesn't exist, this will fail at runtime. For the Vitest worker, we don't know what modules we'll be importing until we start running tests. We need some way to define a fallback if the module isn't found in the registry. And that's exactly where the module fallback service comes in. This is a new thing we added to workerd, which, if enabled, unresolved imports become HTTP requests, including the specifier and referrer. We also include whether this was an import or require, as these have different semantics. The service can then respond with a module definition or a redirect to a different specifier if the resolved location is different from the target. Requires are synchronous, so these will block the main thread until the service responds. This is sort of like how modules work in the browser. Our implementation instead sort of implements Node-like resolution with support for automatically detecting named exports in common JS modules like Node. And with that, we have everything we need for dynamic code evaluation. We can run arbitrary code with unsafe eval bindings, and we can import arbitrary modules with the module fallback service. These features enable many other use cases for us. We're effectively building a custom Vite runtime here, which could be used in the future for meta framework dev servers, which will allow you to have hot module reloading for your server code while still having access to all of the Cloudflare bindings. Now that we can run and import arbitrary code, the next step is to get Vitest's test runner executing inside of workerd. Let's go back to how we usually write workers. This worker does some background work, then logs to the console. except if you run it, it doesn't. If you send a request to it, you never see the console log. And this is because every incoming request in Workers has its own request context. Asynchronous I/O, like fetch requests or timeouts, needs to be performed within a request context. And when a response is returned, the request context is automatically disposed, and all pending async I/O is cancelled. In this case, the set timeout is automatically cleared. This limitation allows us to improve overall performance of Workers. To fix this, we need to extend the lifetime of the request context until the background work is complete. This is quite problematic for tests, which have lots of async operations. We don't want to have to wait until we don't want to have to add this wait until thing to all of them. Fortunately, we also have these things called durable objects. Durable objects are essentially instances of JavaScript class distributed around the world. Each instance has a unique ID and its own persistent storage. Instance properties can be used as volatile in-memory storage. If you're familiar with actors, it's kind of like those. As an example, you might define a durable object class for a user in your application, and then each user would have their own instance of the object located closest to them. Let's walk through an example. Say we're building a collaborative document editor. We'll define a durable object class for a document. This is just a regular JavaScript class with a special fetch method for handling requests. And let's say I want to create a new document. If I use the new unique ID function to get a durable object ID, in this case 09f, and because I know this ID is unique, I know that no other object exists in the world with that ID. So I construct an instance of the class in the data center closest to me. Now let's say my colleague in the US wants to create a document. Instead of using new unique ID, they call the ID from name function, which effectively hashes a name into a durable object ID. Because we don't know whether an object with that ID already exists, the system first has to do a global lookup. Now that we're confident the object doesn't already exist, we can create a new instance, again in the closest data center to my colleague. And finally, let's say I have another colleague in Australia. They'd like to access my document, so I share the ID with them. They use the ID from string method to get a durable object ID, and then connect to my already existing instance. Because they're already on the other side of the world, their latency is quite high. We haven't implemented this yet, but in the future, we're hoping to allow durable objects to move, so they're roughly equidistant from all connected clients. So this would look something like this in this case. It might move to India to be closer to my colleague. Let's look at what the code might look like for a durable object. Fitting a collaborative editor into a slide is pretty tricky, so let's stick with the simple request counter. Whenever a request comes in, we hash the request URL into a durable object ID, and then we get a stub to that object and forward requests to it. The counter instance will increment and return its new count. The important thing for us is that durable objects reuse the same request context for all requests and auto-extend their lifetime. So by executing the test run inside a singleton durable object, we don't need to worry about calling wait until. This is great for long-running requests like WebSocket connections, and with this in mind, what we want is a durable object that terminates a WebSocket connection, imports the Vitest worker script, then uses WebSocket messages for RPC. This is a durable object that just does that. We'll start by creating a WebSocket pair, which is a non-standard Workers API, kind of like Message Channel, but for WebSockets. You keep one half and return the other half in the response. Then we extract the data for this worker from a header, using a more advanced version of JSON.parse that supports structured serializable types with circular references. We then use a custom WebSocket message port class to adapt a WebSocket with a message port-like interface, again with support for structured serializable types. We're still trying to run code designed for Node here, but luckily we have this Node.js compatibility flag, which enables support for a subset of Node's built-in modules, and then by polyfilling a few more built-in modules with the module fallback service, we're able to get Vitest running in Workerd. This enables us to run tests that import basic functions, call them, and assert on their return values, which is a great start. But what about those env and context parameters from earlier? How do we write tests that depend on them? For this, we'll define a Cloudflare test module that gets returned by the module fallback service. We use a module level variable for storing the current environment and export a function for setting this. Our Cloudflare test module re-exports a subset of an internal module so users can't mess around with hidden things. The env variable is set using the second parameter to our runner objects constructor. And with that, we kind of have integration tests. We're able to import worker handlers and call them directly, but remember what I said about request context earlier? The test runner is running inside a durable object context, so we don't have to worry about wait untils. Because we're calling worker handlers inside that context, they also don't have to worry about wait untils, which isn't really what we want from an integration test. We'd like the behavior to match production. Instead, we allow users to configure a main entry point. In the worker implementing the runner object, we define a handler that imports their entry point with Vite and forwards the call onto their handler. Because we're importing with Vite, we get hot module reloading for free. When main or one of its dependencies change, modules are invalidated and tests rerun with new code. We then define a worker binding to the current worker in the Cloudflare test module named self. Using this gives us a more ergonomic API for integration tests. You don't need to worry about passing env or CTX, and request context limitations apply correctly. The cool thing about this is that the worker is still running in the same global scope as tests, so global mocks still apply to it, and if we were to import the main module in this file, it would be exactly the same instance as used by the wrapped handler. So to summarize, durable objects are insanely powerful. We've barely scratched the surface of what's possible here. We define a Cloudflare test module with helpers for accessing bindings, creating execution contexts, and performing integration tests with self. So we basically have everything we need to write unit and integration tests for workers now. The next few sections are about how we added some additional functionality to improve the developer experience. Let's start with isolated per test storage. Most workers' applications will have at least one binding to a Cloudflare storage service, such as KV, R2, or T1. Ideally, tests should be self-contained and runnable in any order or just on their own. To make this possible, writes to storage need to be undone at the end of each test, so reads by other tests aren't affected. While it's possible to do this manually, it can be tricky to keep track of all writes and undo them in the correct order. For example, take the following two functions that get and push to the provided list. Ideally, we'd write tests like this, using the same key in both tests. Note that the push of 2 to list A has been undone before the second test. When we get list A in the second test, we don't see 2 in there. We can implement this with some additional code before our tests that stores the value of each list before the test, then restores it afterwards. This is quite a lot of work though. It's slightly easier with the recently introduced onTestFinish hook to Vitest, but we still need to remember which keys were written to, or enumerate them at the start and end of the tests. You'd also need to manage this for KV, R2, durable objects, caches, and any other storage service you use, and this is all very error-prone. Ideally, the testing framework should just manage this all for you. And that's exactly what the Workers Vitest integration does with the isolated storage option. Any writes to storage performed in a test are automatically undone at the end of the test. To support seeding data in before all hooks, including those in nested describes blocks, we use a stack. Whenever we enter a test or describe block, we push a new stack frame. All operations write to the topmost stack frame, and whenever we exit a test or describe block, we pop the top stack frame. To demonstrate this, let's simplify the helpers from earlier to always read and write from the same list. We start with a single root stack frame. All top-level before alls write to this frame. When we start a test, we push a new frame onto the stack. This means each test gets its own storage environment copied from the parent. All write operations go to the topmost frame. In this case, the before each writes to the test's frame. As do any operations in the test itself, so we're pushing 3 to the topmost frame here. When a test finishes, its frame is popped, and we create a new frame for the next test. And this means that all changes performed in that test are automatically undone for the next test. Test B will write to its frame, and then we'll get that popped when the test finishes. For describe blocks, the same process applies. When we enter the describe block, we push a new frame to the stack. All before alls in the describe block will write to this frame, and note also that all before alls run before eaches. When we start a new test, we push a new frame to the stack, then run top level before eaches, then the describe level before each, and then the test itself. Note all of these operations write to the test's stack frame. So when the test completes and the frame is popped, all writes are undone, whilst preserving writes from before alls at the top level and in describe blocks. The next test will do exactly the same thing, and then when that test finishes, we'll pop the top frame. Then when the describe block finishes, we'll pop the next frame until we're left with the root frame again. Miniflare implements simulators for storage services on top of durable objects with a separate blob store. When running locally, Workerd uses SQLite for durable object storage. To implement isolated storage, we implement an on-disk stack of SQLite files by backing up the databases when pushing and restoring backups when popping. Blob stores are implemented as a separate store and are retained through stack operations. These get cleaned up at the end of test runs. While this works, it involves copying a lot of SQLite files, and we'd like to explore using SQLite save points for a more efficient solution. To actually trigger pushing and popping, we use a custom Vitest test runner, which allows you to hook into different Vitest lifecycle hooks. In this case, we push the stack before running a describe block or starting a test attempt, and pop the stack after finishing a test attempt or describe block. I've mentioned durable objects a few times now, so let's think about how we would actually test them. We want to be able to unit test durable objects like regular JavaScript classes. This means calling and spying on methods and accessing properties. It would also be useful to have direct access to storage for seeding data and asserting on side effects. Unfortunately, we can't just construct instances of the class. This would break the uniqueness guarantees of durable objects. Durable objects also have fairly complicated implicit locking behavior, which would need to be reproduced when calling methods. You also can't perform asynchronous I/O on behalf of a different durable object. You must be in its request context. To solve all of these problems, we wrap durable object classes in a similar way to regular handlers like we did for integration tests with self. Then we add a special request handler to run arbitrary functions in the durable objects context. Let's see what this looks like. In the Cloudflare test module, we define a run in durable object function that accepts a durable object stub and a function to run. This function expects the instance and persisted state as arguments. We store the function in a module level map and send a request to the durable object with the ID we stored it as. In the durable object request handler, we check whether the ID was set. If it wasn't, we forward the request on. If it was, though, we extract the function from the module level map and run it in the durable object's context. Note we're using the same map here as before, and relying on the user's durable object running in the same isolate as the test runner. We store the result of the function in the map, and then back in the main function, we read and return this back to the user. This addresses all of our requirements from earlier. We can now call methods and access properties on instances directly. We also have direct access to storage for seeding data, and importantly, the callback function is executed in the durable object's request context. Finally, let's quickly cover how we handle mocking outbound fetch requests. Most workers will make outbound fetch requests. It's often useful to mock responses to these requests so you don't have to test against production or spin up additional testing servers. In Miniflare, we allow you to specify an Indici mock agent to route all requests through. Indici is the package that powers Node's built-in fetch implementation. The mock agent class provides a declarative interface for specifying requests to mock and the corresponding responses to return. This API is relatively simple, whilst being flexible enough for advanced use cases. To implement this in our Vitest integration, we bundled a stripped-down version of Indici containing just the mock agent code. In our special bundle, we expose hooks for setting the global dispatcher. We then monkey patch the global fetch function to pass through the mock agent if it's enabled. Let's look at some examples of how this works. When the mock agent is disabled, we bypass it completely and forward requests to the regular fetch function. If the mock agent is enabled and the request matches one of its interceptors, it will return a response. If the request doesn't match an interceptor, it will pass through to the original fetch function, unless we call the disable net connect function on the mock agent, which prevents network calls if requests aren't mocked. In this case, the user would see an error. As I mentioned, we implement this with a custom bundled version of Indici. We use a weak map to store the original request for the original fetch function if the request isn't mocked. And similarly, we use another weak map to store the response from the original fetch function that we can return later. Then we monkey patch the global fetch function. We check whether the agent is actually enabled and pass through to the original fetch function if it isn't. Then we convert the standard request object into an Indici-friendly format and store the original request in the weak map keyed on the Indici dispatch options. Then we define Indici dispatch handlers that record any mocked response we receive. These functions won't be called if the request isn't matched by the agent. Then we define Indici dispatch handlers that record any mocked response we receive. These functions won't be called if the request isn't matched by the agent and calls the original fetch function. After, we define the onComplete handler. This will be called when the full mocked response is returned, or when a response is returned from the original fetch function. If the original fetch function was called, we can get the response from the weak map, again keying on the dispatch options. Otherwise, we construct a standard response object from the mocked returns. Finally, we dispatch the request through the mock agent and return the response promise. And with that, we're done. We've covered how Vitest works and can customize its behavior with custom pools, how we added support for dynamic code evaluation to our runtime, using those primitives to run Vitest inside the worker's runtime, how we improved developer experience with isolated storage, calling durable objects directly like JavaScript classes, and finally, declarative request mocking with Indici. I'd encourage you to try out Cloudflare Workers if you haven't already. You can find a written overview of this talk on the Cloudflare blog, and all the code for the integration is in the Cloudflare Workers SDK GitHub repo. Thank you all for listening.